let's enter the world of quantum computing. I think it would be helpful if we can just define it first so I can create the context for all the subsequent questions to follow. What is quantum computing?
Yeah, so quantum computing is a proposal for using the laws of quantum mechanics, which, as we discussed, are sort of the basic operating system for physics for now 100 years, pretty much exactly. But they're a proposal for how to use these quantum mechanical laws to build a different kind of computer, one that would exploit nature to do computation in a new and different way. And what's the point of that? Okay, well, the first thing to say is that quantum computers would not change the limits of what is Turing computable. Okay, so anything that is computable by a quantum computer, like any function that a quantum computer could compute, could also be computed by a conventional computer. Okay, but there could be an absolutely tremendous difference in speed. Okay, so and this is really the key. Okay, because the key thing that quantum mechanics says about the world is that to keep track of the state of a physical system, you need to keep track of what's called a wave function, right? And a wave function is sort of a much, much vaster object than we have intuitions for. Okay, it basically it assigns a number, actually a complex number called an amplitude, to every possible configuration that you could see a physical system have when you looked at it. Okay, so let's imagine, for example, that I have 100 atomic nuclei. Okay, and each one can store one bit of information. Okay, so for example, it might store it by spinning, by the direction of its spin about some axis, that it could be either clockwise or counterclockwise. Okay, so in this way, using 100 nuclei, I could store 100 bits of information. And so the number of possibilities for how those bits could be is 2 to the 100 power. Right. Okay. But now what quantum mechanics says is no, that's what you see when you look, but that's just a tiny, tiny, tiny little sort of pinhole, vision, pinhole view of what is really there. Okay. What's really there is one amplitude for every possible configuration of these 100 particles. Okay. So if these can be in a quantum state, or in other words, if these can be the quantum version of bits, what we call qubits, right? Then actually you need to, just to specify the state of these 100 nuclei, you need 2 to the 100 power parameters. Okay, so you need one parameter for every possible sequence of zeros and ones that you could see when you measure all 100 of them. Okay, so you could imagine that nature off to the side somewhere has to store some vast scratch paper, that is just way bigger than anything that we directly see, right? For 100 particles, it's 2 to the 100 numbers. For 1,000 particles, it would be 2 to the 1,000 numbers. Okay, 2 to the 1,000, by the way, is much more than the number of subatomic particles that there are in the whole observable universe, which is only like 10 to the 85 or only. So, only like, less than 2 to the 300 power, right? So nature has to, maintain this enormous scratch paper. And then every time something happens to the particles, nature has to cross off all of those numbers and replace them with new numbers, right? So this is a staggering amount of computational work for nature to be going to keep track of these few measly particles. Mm-hmm. And so the original thought that led a few physicists like Richard Feynman and David Deutsch to the idea of a quantum computer 45 years ago was, if nature is handing us this computational lemon, if it is being so hard to simulate on our computers, why don't we make it into lemonade? So why don't we build a computer that itself would have this exponential number of amplitudes? And of course, then they immediately face the question, well, supposing that you built that device, what they called a quantum computer, at the time, this was just a thought experiment, but supposing you built it, what would it be good for? Okay, at the time, they really only knew one answer to that question, which was, well, it would help a lot for simulating quantum mechanics itself. Which indeed is a major, major practical problem that chemists and physicists have been dealing with for generations, right? Some of the highest power computers in the world, including a supercomputer that we have here in Austin called Stampede. A lot of what they are used for is solving the Schrodinger equation, which is the basic equation of quantum mechanics, which tells you how these amplitudes change over time, right? And the reason why this is so expensive, why we need to throw such powerful computers at it, is this exponentiality, right? And so even with the most powerful computers in the world, the chemists and the physicists and the material scientists have to resort to all sorts of hacks and approximations, right? And and sometimes they can't get an answer that is as accurate as they want. Sometimes they have to actually do the experiment, use nature itself as the computer, right? So the original promise of a quantum computer was that you would have a programmable device that could just simulate any quantum mechanical system, of your choice, and that could do it without this exponential slowdown that comes from the fact that you've got exponentially many of these amplitudes that you need to keep track of. Okay. So that was the idea. Now, quantum computing started to enter the public's consciousness, I would say about 30 years ago, which was when an extremely famous algorithm was discovered called Shor's algorithm. Okay. And what Shor's algorithm showed for the first time was that there is a practical problem that's got nothing to do with quantum mechanics, and yet where a quantum computer would make a decisive difference in solving it, right? Okay, that problem was factoring huge numbers, right? Finding the prime factors of, let's say, a 5,000-digit number, right? And why do we care about that? If we're not number theorists, why do we care about factoring numbers into primes? Well, it so happens that the encryption that protects most of the modern internet is based on the belief that factoring is hard, okay? Or that a few closely related problems in number theory are hard, that you can quickly recognize the answer. It's easy at least with a computer to check that, yes, these numbers are the prime factors of this number. You can multiply them. You can check that they're prime. But if someone gives you the product, then to factor it into primes, that may take millions of years, even with a supercomputer, right? So the whole system that we use, called RSA, public key cryptography, it's a beautiful, beautiful protocol that was invented in the 1970s. Okay, but it all depends on the belief that factoring and a few related problems are hard, right? And so what Shor showed in the 90s was that if someone could build a truly scalable, and fully programmable quantum computer, then that would no longer be the case.
How would a classical computer solve the problem of having a large number n and finding the prime factors? How would a quantum computer do it?
Good. So with a classical computer, the obvious approach would just be to try every possible divisor one by one. You say, does 2 go into it? No. It's odd. All right. Does 3 go in? No. 4? Well, all right. I already tried 2. Does 5 go in? Right. And then you could try all the way up to n. Or if you think about it slightly more, you realize, I only have to try up to the square root of n. Right. Because if there was a divisor greater than the square root of n, then there would have to be a corresponding one that was smaller. Okay. But even then, if I have a number with 1,000 digits, well, its square root has 500 digits, right? So I'm still trying, all numbers up to like 10 to the 500 power. That still takes much longer than the age of the universe. Okay. So, after like a half century of effort, right, mathematicians have devised methods for factoring huge numbers on a classical computer that are somewhat better than that. Okay. The best one that's known, or at least that's publicly known, Whether the, NSA or some other intelligence agency knows something better, I couldn't say. Okay. But the best thing that's publicly known is called the number field sieve. It uses some high-powered math, some ideas involving elliptic curves. Okay. But it still takes time that is exponential. So like naive factoring would take time that's exponential in the number of digits of the number that you want to factor. The number field sieve takes time that is exponential in the cube root of the number of digits. Okay, so it's milder, and that is presumably what intelligence agencies are going to use if they want to break, let's say, RSA encryption with a 1024-bit key. Right. But even the intelligence agencies probably can't do it with, let's say, a 2048-bit key. Right. That seems prohibitive even with the number field sieve. Right. So, so it's because that's the best algorithm that we know that, we can still use these systems. Right. We just set the keys to be large enough that it's prohibitive to break them using these algorithms. And then we hope and pray that no one that no one knows a better algorithm, or no one will be able to find a better algorithm than that.
And no one's been running it for 150 years.
Yeah, exactly. Or or ideally, 10 to the 50th years or whatever, right? So yeah, but this is sort of the rickety foundation that the whole security of the modern internet is based on, right? And we always knew that, okay, this is based on assumptions that we don't currently know how to prove. Right, like no one knows how to prove that factoring is a hard problem for a class, even just for a classical computer. Right. What Shor showed, dramatically, was that if someone could build a quantum computer, then that specific assumption is not true. Right, there is a fast quantum algorithm for factoring. Okay. And, Shor's algorithm was such a dramatic development. I mean, it was, I would say, one of the, 2 or 3 most dramatic scientific developments of my lifetime, in my personal opinion. I'm 43. Right. Okay. But it was so dramatic that, when people, tried to explain it in the popular press, right, they constantly wanted to round it down to, well, a classical computer is limited to just trying all possibilities one at a time, right? A quantum computer, its advantage is it can try everything in parallel, right? It can just try everything simultaneously because that's what quantum superposition means. Right. And so Shor's algorithm would work by just trying every possible divisor simultaneously, in another parallel universe or something like that. Okay. So first of all, if that were really how it worked, then that's good for way, way more than just this specific problem of factoring numbers, right? That would change, pretty much everything in the world, right? AI, finance, everything, right? And so then, this sort of misconception took root, which has been so hard to dislodge, ever since, that indeed that's what a quantum computer would do. It would just dramatically speed up everything.
This is the header of your blog.
Yeah, it is, right? But then, secondly, we can point out that, like, if it were that simple, if that were all there is to Shor's algorithm, you just try every divisor in parallel, then why did you need Peter Shor to think of that? Right? It's like, that seems kind of obvious, right?